Okay, thank you. Thanks to the organizer for putting this together, and especially to invite this special session with the biosimia. The work we will present with Bruno Delord is about frontal neural dynamics and timescale for decision making, and it's basically taking together the work of 3 theses from Vincent Fontanier, Mathieu Sarrazin, and Frédéric Stoll, who are the hard worker in this thing. So in the lab, we are very interested in how primates, human and non-human primates, are exploring the environment and how they make decisions to gather information from the environment, take this information to improve and adapt their decision in the long run, right? So this corresponds to an ensemble of processes that work at what we think different timescales, behavioral timescales. So when you explore the environment, you find things, so you can react directly to what you just found. So for instance, food, if you're foraging for food, but also you want to integrate in the long run the information you find across different places in this environment to build some sort of values of the different places and to build a map of the environment. So here I want to contrast right away this difference in time scale at the behavioral scale. And we know from human and non-human primates studies that there are dedicated networks in the brain that collaborate and that elaborate these functions for exploratory behaviors. And as Céline and Guillaume just showed, that there is a strong correspondence between human and non-human primate brain organization. So it's a very interesting to combine this data. Within this brain areas, these large-scale networks that contribute to cognition, there are sub-networks. For instance, a network called the multi-domain network, or the global workspace, as Stan Dehen put it, which is particularly engaged in exploration and learning and higher load cognitive activities. And within this network, I will focus on 2 areas, which is the mid-cingulate cortex and lateral prefrontal cortex, the mid-cingulate cortex that Céline actually just mentioned. We know that these 2 areas are highly connected. They collaborate during exploration and learning, and during decision making, they are connected, but they contribute to different aspects of decisions. They contribute to feedback processing, so outcome integration, strategy switching, planning, value-based decision making at different levels. So our goal basically in the lab is to try to understand this collaboration, this network functioning, and how this functioning contribute to behavior. So speaking of time scale, there's been recently some studies coming from, in particular, Zhaojing Wan's lab, which show that if you look at the firing properties of different cortical areas in macaque brain, so this is also a collaboration between modelers and neurophysiologists using non-human primates. If you look at what they call intrinsic timescales, which is basically looking at the autocorrelation of the firing rate in these neurons in different cortical areas here organized from posterior to anterior levels, you can see a sort of linear trend, a sort of hierarchy of timescales from sensory area to more prefrontal and medial areas like the MCC. And these studies showed and reproduced in different data sets actually that the MCC has larger timescales than TLPFC. And this, we want to argue here, this difference between the MCC and PFC contribute to their functional specificity and might contribute to their role in building exploratory behavior. So in this talk with Bruno, we will show first that how MCC and PFC contribute to different aspects of exploratory behavior. So this is going to be the first part. Then I will show that the activity of different unit types recorded in these regions display different temporal signatures. And finally, we will show, and that's going to be Bruno's job, we show that actually we can demonstrate using modeling and simulation that AHP and GABA B conductances account for these different temporal signatures and for the network dynamic specificities that one can find in MCC and the LPFC. And maybe that can explain actually how they contribute to behavior. So before going there, I need to go through behavior, and because that's what we do in the lab. We first train monkeys to do tasks, and this is a particular one that was designed by Frederick Stoll during his PhD. In this task, we try to have monkeys make different types of decisions. So the task is, so the monkey is interacting with the touchscreen. On the touchscreen, we present different types of items, visual items that the monkey can interact with to work in the task. And the task is divided in trials, successive trials, and a group of trials are forming blocks, and you have several blocks in the session. At each trial, at the beginning of each trial, the monkey is facing a first choice between these two items. If he's selecting the triangle here, he's starting what we call a work option. This is a cognitive task, sort of simple visual categorization task. I don't enter into details, it's not important, with different levels of difficulty, which lead or not to a juice delivery, which is a positive or negative feedback, depending on the performance of the animal, okay? So in this trial, the animal gets or not a reward at the end of the trial, and then he's facing the beginning of the next trial in which he has the option between, again, this triangle and circle. The specificity of this design is that we implemented a system in which each time the monkey is gaining a reward, is making a point in the main task, we're increasing a gauge which rise up with the performance of the animal up to a maximum point at which the animal can get a bonus reward. And this bonus reward is 7 times the size of this reward. So we don't see this gauge here, but the animal can actually observe this gauge and then know how close he is to get this bonus reward by selecting the other option at the beginning of the trial. So here, if instead of working, the animal select the other option, which we call the check option. So here the animal is checking. By checking is actually shown the display of the gauge, which is represented by a large circle within which there is a disk. And this disk is increasing from the beginning of the block to the end of the block, depending on the number of rewards that the animal is getting, okay? When the gauge is full, the animal is receiving a bonus reward. Here in this example, the animal checks is seeing the middle size gauge. There's nothing happening apart from this information provided to the animal. It switches off, and there is another trial in which the animal can again at will select the work option or the check option. So the idea, of course, was to stimulate the checking pattern and see how the brain would produce these checking options. And so we did this by varying the speed, which is the number of quiet trials that the animal needs to perform to go from one step to the next in the gauge and to get to the bonus reward. There are 4 different speeds, and the animal doesn't know exactly which speed there is in a particular block. And so checking is a means by which the animal can get the information and adjust his behavior to get the bonus on the right time. So if you want to be performant in this task, actually you have to work most of the time to gain points, but also check once in a while to estimate where you are in this raising of the gauge so that you can capture the bonus at the right moment, okay? So when the bonus is delivered, I forgot to say, the gauge reset to 1, and then there is another block going. So, and the animals actually do exactly this. They work 80% of the time. They select the work option 80% of the time, and the rest of the time, 20%, they use the check option. And what you see in this figure that the checking is actually increasing with the gauge size, which makes sense, right? The closer the animal gets to the end, to the bonus, the faster they check so that they can actually capture the bonus on the right time. The other observation, I won't go into details here, but we actually verified that the animal is indeed using this gauge information to regulate his own behavior. So it's not only that he's checking to see the gauge, when he receives the gauge, when he sees the size, this size is information that the animal is using to adapt in the next trials, okay? So, and this is what we would call a long time scale information, because this gauge representation is carried across trials so that the animal can regulate in time, you know, across this 80% of work trial, is carrying this information in mind so that he can check at the right moment. And the other observation we made is that animals check mostly after correct trials. So this is more like short time scale adaptation. The animals, and this makes sense, right? Because the gauge increased only after a correct reward and not after incorrect trial. And the animal figured that out, and they check mostly after a reward. So this is a short adaptation. Just after the feedback, the animal decides or biased his decision to check on it. So we recorded in these two areas, the MCC, mid-cingulate cortex, lateral prefrontal cortex in monkeys using single electrodes, sometimes simultaneously in the two areas, and we focused on single unit activity, on spiking. And what I will go fast here, what we observed is something that we knew already, is that if you look at the population of single unit we recorded, which were about like 400 neurons altogether, you find that the mid-cingulate cortex here in black is, you can decode whether the feedback is correct or incorrect just after its onset very easily from the population of neurons in MCC, and much less and later in the LPFC, which reproduce actually some data we had previously. What we observed also is that if you look at whether you can decode within the intertrial, so within the feedback and the onset of the options, whether the animal is going to check or work, then you can decode that pretty early, like more than 1 second before the onset of the lever in the mid-cingulate cortex. And it's stronger than the LPFC, and it's also earlier than the LPFC. So you see already that there is a different contribution of these areas to these different elements. I have your picture here. Last thing,
3 minutes, please.
3 minutes, okay. Last thing is, so I'm late. So last thing is that we actually find in neural activity the trace of the gauge size that we observe here using a GLM in the MCC and not in the LPFC. Okay, so I mentioned that timescales might be important in this, and that different information at different timescales can be used by animals. So we were looking at this. So we first reproduce the data from Murray and Georging Wan's lab, showing that the decay of the autocorrelogram on average in the area is larger in the MCC than the LPFC. So the way you do that is that you fit an exponential and you take the coefficient here of the decay of the exponential fit. But this is very difficult measure. It's not very precise, and we saw that there were some subtleties, for instance, in the peak here of the autocorrelogram between the two areas. So we wanted to go further, and to go further, we actually let this method, for which, by the way, we can fit only 40 to 40% of the data. We use the real spike times autocorrelogram for each single unit, taking all the spike from a session and measuring the timing of the spike to spike relationship. I mean, well, you know what is a spike autocorrelogram. And so on this, we fit an exponential, we extract a time scale, a tau, and also the peak latency, something that we can't do with the other methods. And the next things we did is that we clustered single unit activity based on the spikes matrix. And here we selected two clusters, which we refer to fast spiking and regular spiking units from our data set. So for these different units, different areas, we measured tau and peak latency. And what we observed was pretty interesting. Actually, we found that indeed, for regular spiking and fast spiking, when you look at timescales, you see that the distribution is longer in the MCC in black than in LPFC in blue for both type of neurons. However, if you look at the latency, the peak latency, you see that only the regular spiking neurons in the MCC display this long latency compared to the LPFC, and for fast spiking, it's not different. So this big difference here that people were observing in their data, included us, actually come from a specific population of neurons, regular spiking neurons in the MCC. So the question is, how is this contributing? Is this contributing to encoding particular events in the task? And so the way we do this, so I'm sorry, I don't enter into details, and because I'm late already and we don't have time. But what we did is to separate each type of neurons based on their tau, their time scale, using a median split on the population. And we try to decode information from the task in these different populations. So short tau in light gray, long tau in dark gray. And what you see is that if you look at whether neural activity from the population encode feedback, correct or incorrect, you see that only in mostly regular spiking with short tau encode this information, which is actually, I said, on short time scale. And fast spiking neuron actually longer short tau fast spiking encode at the beginning of the intertrial when the feedback is unsettling, it's encoding the feedback direction. However, if you look at the gauge size, the representation of the gauge size, which is indeed carried across trials, so it's more on the larger time scale, longer time scale, and behavioral time scale, then you see that these are the regular long tau population that is encoding this information and not the short tau. So here already we see, and we couldn't find something in the LPFC, which we knew actually. It shows a strong link between the type of neurons, the population, and their intrinsic properties, and how they correlate or they encode information relevant to the task at different times. So the idea then was to understand where is it coming from, and how can we explain the contribution of different time scales to this cognitive function. And that we cannot do with the monkey model because it's too complicated. So the only way we could address this question was using modeling. And that's when we contacted Bruno and Mathieu Sarrazin, and that then started a really great collaboration that Bruno and work that Bruno is going to describe now. And so I'm stopping the sharing.
Okay, thank you very much. We can switch directly to Bruno.
Okay, thank you very much, Manu. Everybody is hearing me and seeing my screen?
We see the screen, we hear you, but we don't see the presentation. We see some. Okay. Now it's okay. Yeah.
Okay. Hi, everybody. Thank you, Manu. So the question here was, can we explain using models of local frontal neurons or local frontal circuits, neural networks? Can we explain these temporal signatures? So meaning the time constant of the autocorrelogram of neurons and the latency of these autocorrelograms, with in mind the fact that Manu has shown to you that these temporal signatures appear to have functional significance. So what we did with Mathieu Sarrazin, the PhD student I'm working with, is develop fine-grained Hodgkin-Huxley cellular and recurrent neural networks, so cellular models and network models of local frontal networks with highly constrained specifications regarding ionic channels, synaptic receptors, the local architecture, you know, the probability of connection between neurons, the probability of bidirectional connections, the distributions of synaptic weights, extra drawn from the literature in frontal areas. Also, the fact that our networks were respecting the balance between excitation and inhibition. We checked that neurons and network models had realistic neurodynamics, being in the high conductance states, in the asynchronous irregular regime, and with physiological spiking frequencies and parameters describing the irregularity of discharge. And our objective was to explore these models and try to reproduce these distributions here on the right. So what you see is bivariate distributions of latency and time constants, time scales of neuronal populations for regular spiking and fast spiking in the LPFC here and the MCC here. So we had to try to reproduce this data, and we look for that using a similarity index between our models and the data in these different models. Basically, what we found in cellular models is that although it is possible in theory that hyperpolarizing conductance can increase the refractory periods of the discharge, then intensity of the autoprogram, while depolarizing conductance can increase burstiness of discharge and then increase latency and the time constant of the autoprogram, while also slow time constant conductances can increase the time constant of the autoprogram. We were unable in most models, like in cellular models using adaptation, very well-known classical conductance regulating the firing frequency of neurons, we were unable to change the latency or the time constant in significant proportions. It was the same for rebound conductances, and it was also the same playing with slow synaptic transmission of inputs towards these cellular models. And the only configuration in which we found something was when we played with what is called the CAN conductance. It's a calcium activated non-selective conductance that is important in frontal, in the cortex in general and in frontal areas in particular, and AHP conductance. Playing with those two conductance, we were able to show that the latency and the time constant of the autoprogram of neurons were affected by these two parameters when we were playing with both together. But although we could reproduce the temporal signature of with our similarity measure in the LPFC, it was not possible to reproduce the MCC temporal signature. So basically, at the cellular level, our models failed, and we switched to network modeling with our recurrent neural networks. And our idea was that perhaps complex network interactions of synaptic and intrinsic properties or dynamics may account for the temporal signatures. We found that using one-dimensional exploration, like playing with only one parameter, one maximal conductance of intrinsic or synaptic conductances or of their time constants, where these explorations were absolutely unable to give a full account of temporal signatures in these two areas. It was the same for most two-dimensional explorations. Why did we do these two-dimensional explorations? We tried that because as you know, interactions are nonlinear in these networks, and it's possible sometimes to get something when you play with two parameters. It was most of the time impossible, but we found that a specific, and that was the sole one, combination of the regulation of slow inhibitory transmission and AHP, which are potassium channels, conductance was able to reproduce these four distributions here. So here you have regular spiking neurons, fast spiking neurons, and you have the distributions for the LPFC, the prefrontal cortex, which is important functionally for executive functions at the trial timescale, and here also for the cingulate cortex, which is important for integrating and monitoring behavior across timescales, so at a larger timescale. We found that GABA-B was, so synaptic transmission was responsible for the increase in the timescale, while AHP was responsible for the increase in latency. In this GABA-B AHP plane, we found that we could separate two robust regions where the similarity to the LPFC and the MCC were important, and that was really the sole couple that was able to do that. Then we asked the question of what could be responsible for these different temporal signatures in terms of neurodynamics of the networks. What was different in neurodynamics? Starting from the visual observation of apparently different forms of asynchronous irregular dynamics, we did a hidden Markov model analysis of collective spiking, and we found that activity in both models were organized into metastable states. That was the first point. Consistent with bibliography since the 90s. So this has been done already on experimental data, and it has been shown that in frontal areas, there is an organization of activity into separated states in the activity space, which is thought to implement cognitive representations, mental representations, internal representations of the animals. It can be perceptive, it can be anticipatory to actions, it can represent rules or internal states of motivation, whatever. I mean, many propositions have been done. Then what we have predicted with the model is that actually states were longer in the MCC, in the singular cortex, which monitors behavior, than in the prefrontal cortex that realize direct executive operations trial by trial. And this prediction actually was observed in real monkeys solving cognitive tasks in the data presented by Manu. Then what we saw in the model and in monkeys was that actually the duration, the stability of states was related to their separation in the activity space. So the stability of states, in fact, is related to the separation of different attractors within the asynchronous irregular activity. That is the separation of neural, I mean, it can be interpreted as the separation of neural representations. Then, and this is the end of my presentation. I don't know how long I have. Then we went to the next idea, which was to try to understand the determinants of this state stability and transitions. We found that as for timescales based on the autocorrelogram of activity in monkeys, we found that GABA-B was responsible for increasing the duration and of states and the separation of attractors. We found also that the AHP, after hyperpolarizing potassium conductance, were controlling the level of short states, which you can see here in the pink and gray curves, which are
everything disappeared. Ah, okay.
Sorry, Fredo?
No, everything disappeared for a while. So it's good. It reappeared now.
Okay, sorry. So basically, inhibition is controlling the duration and the separation of states and attractors. Potassium conductances are, in our models, are controlling the proportion of short states, which are important for transitions between states. What we saw also is that inhibition is actually controlling transition between attractors. When you switch the activity of neurons, either excitatory or inhibitory in those networks, between one state and the other, you can much more easily control transition to other attractors in general using inhibition, and also the selectivity, the specificity of this transition toward a given attractor is controlled much more easily by inhibition than by excitation. So this is my last image. This is the last panel. The idea finally came of a scheme of principles in which, in fact, what we observe with models consistent with our data is that in the LPFC, probably there are smaller and more shallower attractors compared in the LPFC compared to the singular. So in the singular cortex, you have attractors that are deeper and larger, which explain how they could maintain information and integrate it more stably across time, across trials within this context of cognitive work. We also have ideas here about how potassium AHP conductance can help destabilize some of these states to produce transitions or in the MCC or stabilize attractors in the LPFC. So we finish with this kind of functional map with 2 dimensions, which can control the number, stability of states, and give them a functional sense in the context of the differential role of these 2 frontal areas. Thank you very much. This is the end. And thank you especially to our both team with Manu, and to Vincent Fontanier and Frédéric Stoll, which worked a lot on experimental data, and Mathieu Sarrazin, which is finishing his PhD thesis as Vincent Fontanier for the modeling part. Thank you very much.